Hi everyone, welcome back to chemistry. In this video, we're going to be talking about my personal favorite gas law, which is the ideal gas law. And the reason it's my favorite is because it kind of connects all of these different relationships that we've been learning about, plus moles. And I like to think about moles because I love chemistry. I don't know about you, but I love camping. And when I go camping, I've got to bring some butane to use as fuel for a portable gas stove. So what's cool about the ideal gas law is that if you know the pressure, volume, and temperature of the gas that's in your butane tank here, you can figure out with the ideal gas law equation how many moles of the gas are present, or even you can convert from grams to moles. I'm sorry, from moles to grams to figure out how many grams of the gas are present. So I don't know, just kind of cool. So what is the ideal gas law? So it's a combination of the four properties used in the measurement of a gas. So we've talked about pressure, we've talked about volume, temperature, and amount of gas, which we express with N, usually measured in moles, to give one single expression or mathematical equation, which is written as PV equals nRT. That's the ideal gas law. Again, this will be given to you on an exam. But PV equals nRT, sometimes you'll hear it abbreviated as PVNRT. PVNRT, kind of weird, but yeah, it's just a little bit more fun to say, I guess. Or you can just say PV equals nRT, or ideal gas law, where P is the pressure. P is the pressure. V is the volume of the gas. N is the number of moles. R is something called the gas constant, and we'll talk about what that is. And T is temperature in Kelvin, as always. All right, so let's go ahead and talk about what the gas constant is. So R is the variable we use to represent something called the ideal gas constant. And I don't want to go through the derivation with you. You can look at this this part and this part more if you're interested. If you really like kind of the algebra and the math part of it, you might be really interested in that. What I like to just tell my students is R is always equal to 0.0821 liters ATMs over moles Kelvin. Weird units, right? So another way you'll see this is written like this. So kind of weird. The units are liters times atmospheres divided by moles times Kelvin. So liters ATM over moles Kelvin. They look really scary, but actually it's not too bad. Just as long as you kind of remember that your gas constant has those units. And again, this will be given to you on an exam. So don't memorize this value. Will be given on exam. But you do need to know when you're looking at the ideal gas law equation, you do need to know that R is the gas constant. So I'll put R equals this number here on the exam, but you need to know, when you look at that equation, oh, what the heck is R? Oh, that's my gas constant. There's actually a couple different gas constants, but for this class, we're only going to talk about this particular gas constant. Okay, so learning check. So dinitrogen oxide, N2O, which is used in dentistry, is an anesthetic, so hard to say that word, anesthetic, also called laughing gas. What's the pressure in atmospheres, so ATM, right? Of 0.350 moles of N2O at 22 degrees Celsius in a 5-liter container. Whew, okay, lots of different types of things here. Since we're talking about our ideal gas law, I'm just going to go ahead and write it up here. PV equals nRT. Okay, and then I'll just remind you here, this is the gas constant. which is 0.0821 LATM over mole K. We got N is our number of moles. And then the rest, I think, we're pretty used to at this point. Okay, so let's go ahead and start labeling. So it says, what is the pressure in atmospheres? So that's my P value, right? So that's my P in my gas law equation. We got number of moles, so that's N. We got a temperature in Celsius, so that's T, but let's remember to convert to K. And then we've got a volume in liters. All right, so let's go ahead and just like we've done before, let's convert from degrees Celsius to Kelvin, just right away so we don't forget. So we got 22 degrees Celsius, so K equals 22 plus 273. Kind of getting used to this probably. So 22 plus 273 is 295. K equals 295. Okay, so that's my temperature. So we'll go ahead and label that T now that we have it. All right, so now let's do our second step. Actually, let's do it here. So second step is plugging in our values. So PV equals nRT. Okay, what are we solving for? Yeah, P. P is the one we're solving for. We want our pressure. Okay, so we want that alone. So let's go ahead and divide both sides by V, volume. That should be a capital V. Looks a little bit like a lowercase v. Okay, so P equals nRT over V. All right, so now we can go ahead and plug in those values. We got 0.350 moles. Okay, and then we got our gas constant R. So our gas constant R is 0.0821 L times ATM over moles times Kelvin. Okay. You got to put the units in. I know it's a pain in the butt, but it's really important, and I'll show you why in a second. So we got our units in there for our R. So remember, this whole thing is our R. Okay, now we got T, which we just solved for in Kelvin, is 295 Kelvin. Okay, already we can see why those units were so important, why it was so important that I converted, right? Because in order for our Kelvin to cancel out in our R constant, we need to have our temperature in Kelvin. All right, I'll get off my high horse. So now we got divided by all of that, divided by my volume, which is 5.00 liters. Okay, remember, if you were given a volume in mils, you would have to convert to liters. Why? Yeah, because we have liters in our gas constant. Eventually, we want to end up in just units of pressure. Units of pressure don't have liters in them. They don't have temperature units in them. They don't have moles in them. We just want ATMs, right? Okay, so let's check this out. So we've got moles in our numerator. And this is kind of weird, but we've also got moles in our denominator here. So take a look at this, right? We've got moles in our numerator, even though this whole thing is in our numerator for our big fraction. We've also got kind of like a fraction for our units there. So those moles actually cancel out. Okay, then we've got Kelvin in the numerator, right? And then times this Kelvin in the denominator there. So same idea, those are going to cancel. Okay, now we've got liters in the numerator, right here, and we've got liters in the denominator here, so we can cancel those out. I can get rid of my R here. So cancel out those liters and our liters, and we're left with just ATMs. So cool, right? All right, so let's see what that answer actually is. Okay, so I plugged that in my calculator, and it looks like my answer is 1.69, let's see how many, looks like 3 sig figs all around. So let's leave it at let's go 1.70 because my calculator showed 1.695. So I'm going to go ahead and round that to 1.70 ATM. Final answer. Okay, let's just double check that that's what they got. And it is. Cool. Okay, so let's kind of like break this down a little bit or summarize. So we said, okay, we've got a pressure, we've got moles, we've got temperature, and we've got volume. Kind of the biggest hint for me is whenever I see that I've got moles in my question, then I know I'm going to have to use the ideal gas law, because that's the only one of the laws that we learned about that has moles in the equation. Okay, so that's kind of my biggest tip is when you see moles in there, you're probably going to have to use the ideal gas law. The next thing I want to talk about is Dalton's law, which is actually the short way of saying Dalton's law of partial pressures. So this is talking about the partial pressures that different gases in a mixture exert on a container and how you can find the total pressure from that. So let's check this out. So the partial pressure of a gas is the pressure that each gas in a mixture would exert if it were by itself in the container. So each of these gases in a mixture here is going to exert a specific amount of pressure on the container if it's alone. And in a mixture, it actually is going to exert the same amount of pressure. Okay, and that's called the partial pressure. So Dalton's law of partial pressures states that pressure depends on the total number of gas particles, not on the type of particles. And the total pressure exerted by gases in the mixture is the sum of the partial pressures of those gases. So in other words, if we take all of the partial pressures of our different gases and we add them up, we can get the total pressure of the gas mixture. Okay, so if you have kind of a mixture like we did up here of helium and argon, and we know the partial pressures, we can add up those partial pressures to get the total pressure. Okay, and you'll notice that we have kind of like a P here with HE under it. That stands for partial pressure of helium, or just pressure of helium. And then pressure due to argon is PAR right there. Sorry, let me get rid of these other arrows. PAR here, right? So the idea is P total equals PHE plus PAR. So the partial pressure that helium exerts on the container plus the partial pressure that argon exerts on the container, okay, is equal to the total pressure. So, for instance, the air that we breathe every day is actually a mixture of a lot of different gases. It's mostly nitrogen. So remember, nitrogen is a diatomic molecule. So N2 we would just call nitrogen, right? It's in its elemental form. And oxygen, O2, another diatomic molecule, right? So it's mostly nitrogen and oxygen and then some other gases mixed together. Okay, so what we call the atmospheric pressure, right, that we talked about in one of our previous videos, is actually just the sum of all of the partial pressures of those different gases in the air. So in millimeters mercury here, we've got the partial pressure of these different gases. So nitrogen has a partial pressure of 594 millimeters mercury. Oxygen in the air has a partial pressure of 160 millimeters mercury. Okay, and then these other kind of mixtures of gases have a partial pressure of 6 altogether. And so the total air pressure for the air is just going to be the sum of all of those partial pressures. So that's equal to 760, right? So remember, why does 760 sound familiar? Well, 1 ATM, 1 atmosphere, is equal to the atmospheric pressure, which is equal to 760 millimeters mercury. So kind of cool, right? All right, and over here you can just see the percentage that those gases make up in the air. Okay, so how do we actually do these problems? So a scuba tank contains oxygen with a pressure of 0.450 atm and helium at 855 millimeters mercury. What's the total pressure in millimeters mercury in the tank, assuming that we hold volume and temperature constant? Whew, okay, so how are we going to do this? Well, our goal is to find the total pressure in millimeters mercury. So right away I'm noticing this is in atmospheres. So the partial pressure of my oxygen is currently in atmospheres. So let's go ahead and convert my atmospheres to millimeters mercury so that we can actually compare, apples to apples. So how are we going to do that? So we know 1 atm equals 760 millimeters mercury. So let's go ahead and do our conversion. So 0.450 atm times, what do we want? ATM on the bottom or the top? Bottom, yeah, we want to get rid of it. So 1 atm equals 760 millimeters mercury. Okay, so we're going to cancel out that ATM. And we're left with millimeters of mercury. So the partial pressure of oxygen is 0.450 times 760, which is 342 millimeters mercury. I'm going to leave the 3 sig figs. All right, so step 2. Now we actually have millimeters of mercury for our oxygen partial pressure. So let's say we've got, let's go ahead and write our equation. So we know that our P total equals the partial pressure of, in this case, oxygen. So I'll put O2 plus the partial pressure of, what was our other gas? Helium. So He. Okay, so P total is what we're solving for. And we know PO2 is 342 mmHg plus the partial pressure of helium is 855 millimeters mercury. 855 mmHg. So now we can add those together. So 342 plus 855 is 1197. So P total equals 1197 millimeters mercury. Let's go ahead and, looks like we have about 3 sig figs. So let's round this to 1. All right, so I want this number to be in 3 sig figs, and I was struggling for it for a little bit off camera because I'm like, I don't want to round it to a number that's not close to my actual value. So this is where scientific notation can come in handy. So why don't we say the number that we want to express is around 1200 millimeters mercury, right? So I rounded from 1197 to 1200, but I can't get this to 3 sig figs in a way that still expresses the correct number. So I'm going to actually just put it in scientific notation. This is kind of a cheat. So what I'm going to do is there's an imaginary decimal point there, and I'm going to scoot that over 1, 2, 3 to the left until I'm at a number between 1 and 10. So 1.2, and then since I moved it over 3 times, remember that's going to be times 10 to the, what, -3 or +3? Yeah, +3 millimeters mercury. So that's my P total. And now, whoops, the whole reason I did that was so I would have 3 sig figs. So I'm going to add that 0 in there. Times 10 to the 3rd, because now I actually have 3 sig figs here, okay? And remember, when you're looking at a number in scientific notation, the coefficient in front, that 1.20 is telling you how many sig figs you have. So this has 3 sig figs, which is how many I wanted in my final answer. Okay. All right, so that's my final answer. So now let's double check that that's what they got down here. Yeah, they did the same thing. Perfect. Okay. So that is the total amount of pressure that each of those gases is exerting on that scuba tank. Pretty cool. Okay. Now, what if we're solving for a different part of that equation rather than just the total pressure? What if we knew the total pressure and we wanted to figure out the partial pressure of one of the gases in the mixture? We can do it. So this says for a deep dive, a scuba diver uses a mixture of helium and oxygen with a pressure of 8.00 atm. If the oxygen has a partial pressure of 1280 millimeters mercury, what's the partial pressure of the helium, assuming volume and temperature are constant? Looks like we have 3 options here, and they're all in millimeters mercury, so we'll go ahead and stick with that. So let's use our P total equals P of each of our parts of our mixture. So we got PHE for one of our gases. And again, P oxygen, so PO2. Remember, oxygen is diatomic molecule, so anytime you see oxygen gas, you're going to assume that it's O2 unless you're told differently. All right, so now we know that the total pressure is 8.00 atm. So 8.00 atm. Oh, ooh, okay, so I just noticed my total pressure is in atmospheres. So I'm going to have to convert that to millimeters mercury. So let's do that over here. So we got 8.00 atms total for our P total. We want to end up in millimeters mercury. So remember, 1 atm is 760 millimeters mercury. And that's going to give us 6,080 millimeters mercury. And that's because I could cancel out those ATMs. So 80 millimeters mercury is our total pressure. Perfect. So now we can actually use our partial pressure of oxygen and end up with the partial pressure of helium. So PHE is what we're looking for, partial pressure of helium. We know oxygen is 1280. They gave us that, millimeters mercury. So now we just do a little bit of algebra to get PHE alone. So PHE equals 6080 minus 1280, which is going to give us 4,800 millimeters mercury. And that's my final answer. All right, and then your book also gives this concept map about all the different gas laws, so if that helps, you can take a look at that. Go ahead and pause the video, copy it down, look in your textbook, take a picture, whatever works best for you. And congratulations on making it to the very last lecture of the quarter. You guys were an amazing class. I'm really, really grateful that this was my first chemistry class. So I will see you in... I was going to say the next video, but there isn't one. So have a nice rest of your day.